Hello everybody and welcome again to the NPTEL online certification course on microelectronics devices to circuits. As we have in our previous interactions, we have understood basic BJT, which we have already done quite a lot, and then we started with CMOS technology, and to understand that we understood what is a MOSFET technology, and we understood therefore in the previous two slides or previous two interactions or modules what is MOSFET really, the structure of MOSFET and the functionality of MOSFET. So first order we saw that the MOSFET therefore can be recapitulated as a current source when working in the saturation region. It can work as a voltage variable resistor when it is working in the linear region of operation. These two things we have already seen as a device. We have also seen that the MOSFET can be used as a switch when your gate voltage swings above and below the threshold voltage of the device. We have also seen that there are two types of devices, enhancement mode MOSFET and depletion mode MOSFET. In one case the threshold voltage is positive, in another case the threshold voltage is negative. Enhancement mode is also known as normally off device, and depletion mode is also referred to as normally on device. What we will be looking subsequently is the following thing, right, and the topic of today's is transistor basics. We will be going into the part 3 part. Within part 3 the outline of this topic will be, we will be looking at various short channel effects, right. We are looking at second order effect. Short channel effect primarily means that as you reduce your dimensions of the device, what second order phenomena or effects comes into picture, which is detrimental to the performance of the device. That is basically a short channel effect. We will be also looking at body effect and channel length modulation, this is CLM, right, and this happens at extremely low dimensions, and how does it influence the output electrical characteristics of the device. We will be looking into that. We will be also looking at the type of device scaling. Primarily we will be looking into two types of device scaling. One is electric field scaling, and another is the voltage scaling, and we will see its relative advantages and disadvantages. Within short channel effects we will be looking into velocity saturation effects, right. We will be actually looking into drain induced barrier lowering, also referred to as DIBL, right, DIBL, and we will be looking at punch through, which is basically a hot carrier effect phenomena. Then once the MOSFET as a device is clear to me, we will like always this MOSFET to be used in circuit simulation purposes. So can we have techniques of doing some amount of circuit simulation using, so can we have therefore some electrical equivalent models of MOSFET which can be used for circuit purposes. We will also look at basic equations which we need to remember and then recapitulate the whole talk, right. Let us look at the various short channel effects. Now why short channel effect came into picture? See, in 1965 Gordon Moore, he was a scientist at IBM, and he predicted a very important trend very famously known as Moore's law, which is very famous within the semiconductor industry as well as in academia. He stated that for every 1.5 year growth of semiconductor industry, you would expect to see that the number of transistors per unit area will be doubling, right, which means that if the number of transistor per unit area is X today, then after, so if it is at, this is 2019 let us suppose, and then at 20 middle of 2020, right, I would expect to see this the number of devices, active devices per unit area to be equals to 2x, right, and this was given by Gordon Moore, who stated that the number of active devices will increase. And why will it increase? To increase the functionality of the chip and to enhance the functionality of the chip. So those companies or those industries or those people who are able to sustain this Moore's law have been able to increase the functionality of the chip, and therefore the profitability is there once one follows Moore's law. Easier said than done, because then when you want to increase the number of charge carriers, the number of active devices per unit area, the only option available to you is that you reduce the dimension of the device, because your silicon area is always fixed, right, and you cannot increase it drastically beyond a particular point because of fabrication limitations. So the only option available to you if you want to follow Moore's law is that you want to reduce the dimension of the device, right. So how do you reduce the dimension of the device? For example, in a MOSFET, how do you reduce the dimension of the device? You simply channel length, you lower it. So, if today your channel length is 2019 is L, then in the middle of 2020 middle, I would expect to see this to be as L by 2. Similarly, at 2021 end, this should be equals to L by 4, and so on and so forth. So you see, for every, for example, 2 to 3 years of growth approximately, you are almost quarter sizing your device, right. And so the idea was therefore that in case of a FET, for example, when you are reducing the channel length, you are also making the source and drain come closer to each other, right. Now, theoretically speaking, therefore, if you continue with Moore's law, a time will come when that length and drain will touch each other or very close to each other, and there will be shorting. Once the shorting is there, it will not work as a FET anymore. So, therefore, people are trying to find out alternatives to your bulk MOSFETs, so that your performance, electrical performances do not get degraded at low dimensions. So, that is the reason I was saying what is beyond Moore's law, right, and I would recommend that you can have a look at large number of research papers as well as large number of videos on the YouTube, and a large number of open literature which actually gives you an idea what happens beyond Moore's law. Now, therefore, if these dimensions are reducing, then there are certain things which are known as short channel effects which comes into picture. So, that is what is we are referring to, that once the dimensions are reduced because of Moore's law, you have short channel effects coming into picture. The first effect which I wanted to stress in front of you is basically the body effect, right, or also known as substrate bias effect, or also known as body effect. We will come to this as we discuss. Let me explain to you in a very simple terms, and then we can move forward, right. So, if I have p-type substrate, right, and we had discussed this earlier also, I have a p-type substrate and I have got n plus source, n plus drain, and I have got silicon dioxide metal, and then you have gate, source is grounded, right, and then a drain is you are applied a voltage Vd. Now, in the substrate side we generally ground it, for most practical purposes we ground it, but let us suppose we do not ground it and we start giving, let us suppose, a positive bias, right. Now, a positive bias if you give, and if it is an n channel enhancement mode MOSFET, enhancement mode MOSFET, then you can explain to you, as we have discussed this point, Vg should be greater than equals to Vth for the device to be on, which means that there will be large number of charge carriers here. What are the charge carriers? Free electrons, right, will be here, provided Vg is greater than Vth, threshold voltage. But now you have applied a positive bias on the substrate, which means that there is this positive bias will be pulling these electrons towards itself, these electrons will be pulled here. As a result, your gate voltage has to further increase in order to form the channel. So, what happens to threshold voltage? The threshold voltage rises. This is known as a substrate bias effect, that if the substrate which was ordinarily grounded, right, you apply a positive bias in case of an n channel MOSFET, you end up having a threshold voltage increase, right, not a good idea, but that is what is happening. Now, so the idea, the definition is something like this, that when you Vth is the value of threshold voltage without body bias effect, and this is with body bias, and this is with Vsb is basically my substrate source to bulk potential, right, and you have to give the source to bulk potential. We do not have to worry about its sign, you have to worry about sign. If it is source to bulk, source is generally grounded, right, bulk will be given. So, if you give a bulk a positive dimension positive, then source to bulk will be positive. If you give negative, source to bulk will be negative in dimensions or in nature. Gamma is referred to as a body coefficient parameter given by 2 epsilon q into n sub. N sub is the substrate concentration of the doping concentration, and C ox is basically the oxide capacitance per unit area, and phi f is basically my Fermi potential. Right. So, we have understood therefore that this VSB substrate voltage will have an adverse impact on the threshold voltage. So, you actually started with a low threshold voltage and you might end up having a large threshold voltage, which means that you require a larger gate voltage to switch it on, which means that you have larger power dissipation for a particular device, which means that if there is a short channel effect because of body bias, n channel enhancement MOSFET, you give a substrate bias greater than 0, you might end up having a potential or having a threshold voltage which is larger than expected. This is the first thing. The second short channel effect is basically my channel length modulation effect, right, and it is pretty simple and easy to explain, but we will still nonetheless explain each one of them individually before we move forward. So, we have understood what is basically a body bias or a back gate bias. Let me therefore give you an idea about what is channel length modulation effect. See, in our previous discussion when we were discussing devices, we came to the fact that whenever you have a channel basically in our case means that it is basically having free charge carriers connecting source to drain in at least as much it is n type as it was initially p type, right. That is what is basically known as a strong inversion phenomena. Under strong inversion, therefore, you will have direct connectivity path available to you. Now, what you do is that on the drain bias, if you do not give any voltage, then the substrate, then the depletion region on the substrate on the depletion region on the channel, near the channel, this is n plus and this is p. So, if you do not give any bias, this is grounded, this is also grounded, then the depletion thickness will look something like this, it will go something like this and it will be something like this, it will be symmetrical in dimensions, right. Now, if you go on increasing it, time will come when you will have inverted layer here. So, this will be mobile charge carriers, this will be mobile, and you will have fixed charge carriers here, fixed here. Again, we have still grounded our drain. Now, what I do is I do something else, and that is that I increase the value of your VDS. So, I go on increasing the value of VDS, right, and let us see how does it influence the overall current carrying capability of the MOSFET. If you remember yesterday's talk or the previous lecture's talk, you will see that when we were discussing saturation, we saw that this is parabolic in nature and this was happening at VDS greater than VGS minus VTH. This was saturation, right, this was active, right, and this was cutoff. Where what was cutoff? Whenever my VGS equals to 0, I define this to be as cutoff, or equal to threshold voltage, we define the lower value to be cutoff. So, VGS equals to VTH with cutoff. Now, you see at saturation also referred to as active in some of the textbooks. If you look very carefully, this is almost a straight line, which primarily meaning that the current is constant independent of the voltage, right, and it starts to behave like a constant current source. But in reality, we will see that the channel length modulation effect does not allow you to do that. Let us see how. So, as you make your drain voltage higher and higher, the depletion thickness here becomes larger and larger, and it starts to eat away into the channel, and as it starts to eat away into the channel, you see the inversion charge is only restricted up to this much point. However, if you did not have applied any bias and your drain voltage was 0, your inversion layer would have been something like this, right, all filled up with free electron. But now, since you apply a drain bias which is quite large, the depletion region itself eats away into the inversion layer, and your effective inversion charge carriers are shifted from this region. So, the channel length which was initially till this to this point, from this to this point, has actually reduced by a factor delta L, and therefore, the effective channel length is L minus delta L, right, and therefore, if you define channel length as that length at which the inversion charge is available, then by that definition you will automatically have a reduced channel length which is given by L minus delta L at this particular point, right, which means that therefore, if I give a potential VDS sat is the saturation drain to source voltage, then VGS minus VTH is the voltage drop till this much point, right, and the extra VDS sat which makes it saturation falls across this region. So, this delta VDS, which is VDS minus VDS sat, is the voltage which is required here. For example, let us suppose to form, this is 2 volts. So, VGS minus VTH to require to form is 2 volts, right. So, I require my VDS should be greater than 2 volts for saturation, fine, that is okay. But then if I give 3 volts VDS, then out of the 3 volt, 2 volt actually goes to form this channel, right, this channel, and the rest 1 volt appears across this particular region, fine, and that is known as delta VDS, or which is given by VDS minus VDS sat, right. As a result, if you look very carefully, therefore what I will see here is, so I had, so now my depletion, so my inversion layer was somewhere here. When you apply VDS say equals to 2 volts, you increase it to 3 volts, the inversion layer further comes down. It was initially here, now it is here, which means that the effective channel length is actually reducing. It was initially it was this much, right, now it became this much, right, and now further increasing VDS became this much, fine, which means therefore that current which is proportional to W by L, right. So, L is decreasing with increasing VDS, which means that the current is rising, and therefore assuming that current is constant in saturation region is a wrong assumption, and therefore the current will actually show an increase. So, it will show an increase. This increase is primarily because of an increasing VDS and reduction in the effective channel length. That is what is shown here, and therefore the drain current is approximated as this value. Remember, if you remember the previous talk, it is mu n C oxide W by 2L into VGS minus VTH whole square. We have an extra term here which is 1 plus lambda VDS, right. Lambda is defined as the CLM parameter or channel length modulation parameter. It is an empirical constant varying from 0 to 1, and VDS is the applied voltage which you see. So, if lambda is equal to say 0.5, then for every increase in VDS I would see that 50% of VDS will be responsible for increase in the current at higher values of drain voltage, and therefore from the IV characteristics of the MOSFET, what thing becomes clear is that the current will increase with increasing voltage, right. The current will go on increasing with increasing voltage, otherwise you are not allowing to do that because you are making it fixed value of voltage, right. So, that is what is known as channel length modulation effect. Now, coming back to therefore to the basic concept of device scaling, we have two types of device scaling. That scaling will be, one is known as a constant field scaling or electric field scaling, and we have constant voltage scaling which is available with us. Now, scaling does not only mean scaling the channel length, right. You scale when you do a structural scaling, when you scale up or scale down, you scale up everything. So, you scale down channel length, you also scale down the oxide thickness, you scale down the metal contact, you scale down the source contact and the drain contact. So, everything is being scaled down or scaled up, right. So, it is not just the channel length which you are doing it, it is together. Now, the constant field scaling primarily means that in this case we assume, what we do is that as we scale down your dimensions, we also take into consideration that the electric field remains constant, right. To do that, you have to scale down your voltages in a straight away fashion, so that V by L is constant, right. V by channel length or V by dimensions are always constant. What is constant voltage scaling? Well, this is a preferred scaling technique as it provides voltage compatibility with other technologies. Due to this, the cost you pay for it is that you start in the first case, whereas when you lower your channel length you also lower your VDD. In this case you do not do that, you keep your voltage constants, right. When you keep your voltage constants, then the electric field enhancement is there, mobility reduction is there, and so on and so forth. But then it is compatible with technology. So, if you want to work with an anti nanometer technology, if I use a VDD of 0.9 volt, well, I do not have to do any scaling and it will work, give me an optimized result available to me, right. So, for a single amount of scaling, this gives me a very well defined result as far as this device is concerned. We come to the velocity saturation part. As we have discussed earlier, that the velocity of the charge carriers is proportional to the electric field. So, VD drift, this VD is known as the drift velocity, is equals to mu mobility of the charge carriers multiplied by the electric field, right. However, for a short channel device, the electric field in the longitudinal direction and the horizontal direction are both and transverse direction are both equally high, right. And therefore, this linear relationship of VD equals to mu times E is not valid anymore, is not valid, right. Why? Because now the electric field is not only in this direction very strong, it is also very strong in this direction. So, under the influence of these two, you will have a new value of VD, and that value of VD is given by this formula which you see in front of you, given as mu into E upon 1 minus E less than EC, where EC is the critical electric field. So, critical electric field is defined as that electric field after which the mobility is constant or after which the velocity is constant. So, if you plot electric field velocity versus electric field for silicon, it looks something like this. So, this much point, since V versus E is always constant, or maybe this much point, right, this is almost a linear profile. So, mobility is constant. Beyond this, the mobility starts to decrease, and beyond a particular point the mobility is actually very low or very small, and Vsat is typically very large. Vsat is the saturation velocity which you see. Now, Therefore, you see that your Vd here is equals to Vsat, right, and that is understandably so that the applied drain voltage is almost near the saturation voltage, and we get a very large value in the increase in the velocity in case of. So rather than the pinch off of the depletion region, I would actually get a pinch off in the velocity of the charge carriers that will result in almost a saturated drain current for a MOS device for short channel effects, because the electric fields are very high, right. Now, if you plot it, then if we evaluate it, we get something like this, that the drain current ID is given by this basic formula. If you remember yesterday's talk, it was basically 1 plus VDS by ECL, and this will give you the value W by L is coming here in VGS minus VTH into VDS and VDS whole square. So, this is for the resistive reason, and therefore, you see ID has a nonlinear dependency on VDS because it is a square term which you see in front of you. Similarly, if you look at this curve, again ID has got a nonlinear dependency on VDS, right, where K VDS is given by this one formula. So, this formula is nothing but this whole thing, right. So, I define K to be equals to 1 by 1 plus this thing and 1 plus VDS by EC into L. EC is the critical electric field, L is the channel length, right. Now, for if actually what is happening is for long channel lengths, K will approach to 1. So, 1 plus 1 is equal to 2, and you and therefore 1 plus 1 is equal 1 plus 1 is equal to 2, and therefore you reach the conventional equation which you have already studied earlier, right, that mu n C oxide by 2 WL into VGS minus VTH whole square, right. So, that is what we reach if provided K approaches to 1 when you have a longer VDS, when you have a longer channel length or a smaller VDS, right, and in those cases we reach to this value in this case. When VDS increases, therefore, as you can see, the device enters into the saturation region. We have already discussed this point. So, what we do is that we replace VDS by VDS sat, right. So, whenever you are sure that the device is entered into saturation region, then the drain to source voltage which we apply is, rather than writing it as VDS, we write it as VD sat, right, and that is VD sat. VD sat means saturation velocity drain voltage. So, I get ID equals to V sat into C oxide W into VGS minus VTH minus ID sat. So, this V sat is again broken down into KVD sat, and therefore, I get this into VDS. So, this is for the nonlinear region, right, for the nonlinear region, and this is for linear region of operation of the device, right, which comes to the final expression, therefore, that if you have a long channel device and if you have a short channel device, automatically the short channel. So, long channel device saturation will take place at a much higher VD sat, whereas for a short channel device it will take at a much lower VDS sat, because short channel you require lesser amount of drain voltage to pinch off the carriers, and therefore, it is much smaller as compared to the first case. We come to another important topic, and that is basically drain induced barrier lowering. At this stage we will not go any further than saying that initially when drain and source are very far from each other, drain has got no influence over the source, but what is happening is as you go on making drain and source closer to each other, then in the change in the drain voltage will also start influencing the source side. So, as you can see here that as you make your drain voltage higher, the channel length, the conduction band diagram, Q into VDS, there is a drop of voltage, right, because into electron you multiply. So, there is a drop in the voltage, which means that you actually saw a larger current, but now you actually see a dip. So, there is always a decrease in the hump. As a result, what happens is that it affects and lowers the threshold voltage. The reason being your built in voltage is reduced, right, and because of Dibble or a DIBL effect, as a result your charge carriers are more and more and current becomes more and more, right, and it affects the charge distribution model for this case. We come to the last part, and that is basically your punch through. What happens in a punch through is that if you go on increasing, as you can see, as you go on increasing the drain voltage, this depletion region touches each other, right, and this condition is known as punch through, right. So, the charge carriers directly flow from source to drain. So, you do not require a channel, right. If the drain voltage is so high that any electron can be pulled away from the source and it can pass through the depletion thickness and reach the channel, and that is known as the punch through phenomena. For most practical purposes we do not use punch through phenomena in any case, right. So, what we do is that if you increase the value of VDS significantly, then this will happen, but in most of the cases. So therefore, if you plot ID versus VD, then it is something like this, and then suddenly it becomes large. For VDS somewhere here it becomes large. We do not operate generally in this one, but this is known as punch through, which you see. Now therefore, the model which you apply for manual analysis, which means that the model which you will be, all second order effects can be taken care of by a simple tangible analytical model, and the model is that when VGS minus VTH is less than 0 or VGS is less than equals to VTH for an n channel enhancement mode MOSFET, the current through MOSFET is 0, and whenever my input voltage is larger than threshold voltage, then I get ID to be equals to K prime W by L VGS minus VTH V min minus V min square by 2 into 1 plus lambda VDS, right. V min is basically VDS, minimum value of VDS, and lambda is the CLM parameter which you see, and VDS is the drain to source voltage which you see. So V min is basically minimum of the overdrive plus VDS and VDSAT, right. Whatever out of the 3, whichever is the really the smallest one, we assume that to be equals to the value of V min, but typically it is VDS which comes into picture, and it is replaced by a current source, as you can see, with a current ID and a source, drain, bulk and gate. So this is bulk, right, this is drain, and this is gate, and this is source, and this is the drain current which is flowing through the device. So let me see what basic equations you need to remember as far as this lecture is concerned. The basic equation you need to remember is this one, where KVDS is given by this. This is also known as velocity saturation equation, right. In the saturation region, as I discussed with you, the drain current is due to velocity saturation, which is therefore given by VDS sat, and ID equals to V sat into C oxide and W by L, VGS minus VTH minus VDS sat by 2. So once you know the value of VDS sat, you can find the value of ID in a much more detailed manner, right, and that gives you an idea about the various basic equation you need to follow. So equations are exactly the same as you follow for a bulk MOSFET. Small change is that when you do a short channel effect, it is primarily because of velocity saturation, whereas for a long channel effect, it is primarily to do with pinch off at the drain side, right, and therefore these two are totally different issues which you need to find out. Let me therefore recapitulate today's lecture in detailed manner which we have collected. We have understood what is basically a MOSFET technology. We have also understood that the body bias, which is the third terminal body bias, fourth terminal body bias, plays an important role in determining the change in the threshold voltage of the device. Now we have also understood that one of the important effects of miniaturization is the drain and source coming closer to each other, and therefore you will have drain induced barrier lowering, which means that the voltage change on the drain side will influence or will reduce the barrier on the source side, because source side, if you remember, is basically a depletion width is there. Now if I am able to somehow or other reduce the depletion width by by given external bias, and this case happens to be the bias given to the drain side, and the drain is very close to the source side, so any variation on the drain side is replicated on the source side, then we are able to reduce the dimensions, or we reduce the barrier on the drain side, and thereby changing the threshold voltage of the device. The third point is due to carrier velocity saturation, I get the drain current is almost a linear function of VGS, right. So it is VGS minus VTH whole square, and therefore it is a linear function of VGS, right. Well, what beyond Moore's law, we do not know what will happen. There are many alternatives which are coming out, but these alternatives need to be tested in terms of its performance analysis, and more importantly these structures should be able to be, can be fabricated in the current foundries which are available to us, right. So this is the basic idea or a basic concept of the MOS device second order effects, right. So we have dealt with the basic concept, and we have understood the basic idea of this phenomena. With these, let me thank you for your patient hearing, and I will be open for any questioning. Thank you.